So let's think about this slightly adjusted example. So what I've done here is I've just essentially gotten rid of the transitions between states 1 and n, and I had to make another modification, right? I had to patch the probabilities a little bit, right? So I need to make sure that the total probability leaving 1 is going to be 1, and so I just assigned a unit probability of moving from 1 to 2, right? And same thing for going from n to n minus 1, right? So I erased essentially this section here, right? And then that probability had to go somewhere, and I just assigned it to move directly to 2, and the other one to move directly to n minus 1. And so you're welcome to kind of, once we kind of get through this example, you're welcome to play around with kind of modifications and see how, if they work out differently or not. I haven't really thought about it, but that's just a choice, right? But still, it's a fairly small modification of the previous example. This is called a biased random walk on an n path, or at least that's what I just called it. This is n path is kind of motivated from graph theory literature, right? So this is a graph on, or a network, or same thing, a graph is a network on n nodes, right? And so this is a path because you can kind of move only in sequential steps, and you're moving from state 1 to state n, kind of back and forth. And then maybe another name for this would be a biased random walk with reflecting boundaries, right? So because once you hit 1, you immediately shoot back, so it's kind of a reflecting as a boundary. That would be another terminology that's maybe more common in probability theory. So what are we to make of this? Let's try to answer the main question is this thing going to be reversible or not, and what is our intuition telling us, right? The previous example really fell apart when you just kind of ran a few thought experiments. Here my claim is not going to be that simple. So first, when you're developing intuition, always good to try some extreme cases. So we can set p equal to 1 like we did before, and what will happen when p equals 1, and here clearly it's going to go all the way to to n, and so could I tell whether the movie is going forwards or backwards in time? I guess yes, that would be true, but it also depends when the movie started, right? So there's a little bit of a catch here, and I'll try to discuss, maybe let me come back to this at the end of the video. The catch is kind of like, how do we, when does the movie start? If the movie started when the chain was at state, let's say 1, then yeah, then I know exactly if it was played forward in time, starting at 1, right? But at the same time, if I caught it, started taping it later, right, what happens at the end? After a while, this looks like it's going to get trapped between states n minus 1 and n, and it's going to just kind of oscillate. It's going to, well, no, p equals 1, right? So it is going to oscillate, right? It's going to move from n minus 1 to n, and then from n to n minus 1, and back and forth again. And there, if I just catch that segment of the movie, it's going to be pretty hard to tell the difference, right? There's no way for me to tell whether time is moving forward or backwards, right? This thing is moving between n minus 1 and n, and regardless of whether I play the video forward or backwards, there's no way for me to really tell. But if I catch any of the segment where it started earlier on, like let's say it started at state 4, right? If that movie was playing backwards, I will see it go back. I would go 7, 6, 5, 4, right? I would definitely be able to say, oh yeah, that's time moving backwards. There's no way that it did that in the case when p equals 1. So that looks a little bit concerning. We're kind of getting 2 answers, but that's kind of, that's why you make a theory or something mathematically precise. Right here, it's intuition can kind of lead us astray. It can be useful, but it also can point to a couple of different answers as it's doing here. Let's think about when p is not 1, less than 1, but maybe greater to a half. Honestly, I don't know. I know the answer ahead of time, so that makes it have to play act a little bit here, but I thought about this before solving the problem, right? And so I wasn't sure, so my guess was going to be that it is reversible. So like the intuition is kind of like when p is greater than a half but less than 1, clearly there's going to be a bias and the chain is going to be pushed towards that boundary, but then that boundary is kind of reflecting, and so the chain is going to just kind of oscillate here. So at least if the movie is filmed right later on after a long time, then it's going to be pretty difficult to tell whether it's, how do I know if it's when it's moving away from that boundary at n? Do I know time is really moving forward? Maybe not, maybe, right? Maybe not. It is, I guess, in some ways less probable that it moves away from the boundary. So in that case, right, if you're watching the movie and you see that it's maybe more likely to tend towards the boundary, maybe you think, yeah, I'm seeing time moving forward. But it's hard to say though, right? It's hard to say. And as you approach 1, you think like things will be clearer as we approach 1. That's not true, again, because then we'll tend to cycle between n and n minus 1. And then at that point, you definitely cannot tell which direction time is moving. So this one is a bit of a toss-up, right? What I wanted to throw this example in. I designed it specifically to kind of show that sometimes the intuition is only going to get you so far, right? It really got us very far in the previous clip, right? Previous example when we were on a cycle, but here things look much tougher. Anyway, so once you hit this kind of difficulty, you say, all right, well, this is what I have all my equations for, so let's try to get the stationary distribution. Again, I was not able to guess this by intuition. I kind of suspected what it may be from other examples I've seen, but I actually had to work this one through. So here's the way I did it. I did not rely on local balance because, again, I did not know whether it was going to be reversible or not. I guess maybe I could have made that guess and then tried local balance, but I went with global balance equations, and you can try to see if, maybe I should have done local balance here. So yeah, okay. So it's a lesson learned. Maybe I did a little bit too much work, but in any case, this worked out pretty quickly for me. So you get 1 for free, so I chose mu1 is equal to 1. And how do you get to state 1? You can get there from state 2 with a probability transition q, which is 1 minus p, right? So immediately I get mu2. I write my equation for mu2, which you can get to from 1 or 3, right? From 3 you go with probability q, from 1 you go with probability p. Then I solve this. It takes a little, kind of a little manipulation. You'll get this, right? So if you kind of clean up the math, right, you plug in 1 here, you plug in 1 over q here, you subtract it over, you'll see that this is what you essentially get. And then in one more step, you start seeing the pattern right away, right? For mu4, I got, wait, that should be mu3, sorry. No, mu3 is here, mu2, no, this is fine. Yeah, all good. Yeah, this looks good. So, and here you're ready to guess the final form. You do know that mu(n) is going to throw you off a little bit, right? It's not like kind of there is a little bit something to the symmetry argument in that the states between 1 and n, there's no way to maybe prefer one or the other, right? But the states on the boundary are going to have to kind of look a little bit different. So my guess for the states between 1 and n was based on this pattern here, right? This one. And so you see how it matches it, right? When you plug in x equals 4, you essentially get p over q to the 3rd power divided by p, which is what gets me this. And notice there are 2 ways of writing it, right? Either I have a leading 1 over p multiplier or a 1 over q multiplier, and I did that on purpose. You'll see why in a second. But these 2 formulas are clearly the same, right? Identical. And by the way, I should say this is for p not equal to 1. So really, that needs to be said. P does not equal to 1. And then I had to, this boundary came easy, right? This one was the free one, and then this one I had to work a little bit, right? I basically took this equation here, and then I substituted the answer for mu and minus 1, and then I got this one, and it checks out, right? This one meets global balance, and so do all the other ones, and so you're basically done. And now the question is, maybe where I should have done if I was a little bit quicker. maybe I should have started with local balance, and verifying local balance will tell us whether this thing is actually reversible or not. And I kind of wrote it down so that it's so that it's easy, right? You take any pairs of states, right, the ones that have any probabilities of transitioning between two of them, and they're basically going to be one off, right? That it's going to be an x and an x plus 1. So that I have my mu x here, right? And obviously pi x is going to be just normalized, so to verify local balance here, right, I'm just looking for something like this: mu x p x x plus 1 is equal to mu x plus 1 p x plus 1 x, right? That's what I'm, whether I use the stationary distribution or the stationary measure, it's all the same. I just need to make sure this holds. And you can easily see why that's the case, right? In order to go from x to x plus 1, I need to I use probability p, so I multiply by the p, which is why this form is handy, right? And when I multiply by the p, I just get this guy. When I go from mu x plus 1, I chose this form because I need to multiply by q, right? To go from x plus 1 to x, I use probability q, and so you multiply by that and you get p over q to the x minus 1 again, right? And so you get equality there. So we just showed that this does indeed turn out to be a reversible process, at least in the case of p not equal to 1, right? And so whether it's a half or not is not important here. P equals 0.9 gets you reversibility, and at least here that starting from the stationary distribution, the Markov chain, that's this biased random walk on an n path, has exactly the same transition probabilities as its time reverse chain, right? That's going to be the definition. So make sure you kind of square those two. Right here, the Markov chain is equal to its time reversed version. And so now the only thing left that I haven't thought about, but let's see if we can kind of wrap up this case, where p is equal to 1. And to kind of be rigorous, you have to think, well, what's going to be my stationary distribution when p is equal to 1? Well, when p is equal to 1 after a long time, and we basically said this already, but you're going to move between these two states, right, one after another, right? And so, you're kind of equally likely to see, the chain in one or the other state. Of course, you actually know exactly where it's going to be if you know the starting state. But, here it's going to be, should be pretty easy to check that pi of n equals 1/2 and equal to pi of n minus 1 is the stationary distribution. So it's and verifying this is going to be easy, right? You have 1/2 times p, which is 1, is equal to 1/2 times q, which is it's going to be basically pi of n, right, times the probability of going to n minus 1, which is 1, should be equal to pi of n minus 1 times the probability of going to n, which is again 1, right? P is equal to 1, right? So right here, so that's where I got confused a little bit. But so you have 1/2 is equal to 1/2, and so you've just verified that pi n is equal to 1/2 and pi n minus 1 is equal to 1/2 is a stationary distribution. And of course, that leaves pi being 0 on all of these other states. And is this thing reversible? And yeah, basically the answer is yes, because a local balance is trivially satisfied here. And this, why is this? This looks a little bit, kind of, maybe you could say like this is not entirely consistent with the our intuition. You told us that if you watch the movie backwards, you should be able to tell, right? And here, like, clearly, if you start with 1, you'll see that the chain goes all the way to n and then starts bouncing back. So if you started the movie early on, you'd be able to detect the time that's moving forward. And here, if you recall from last lecture, this is where lemma 3 was important, right? It's sort of reversibility is something that is kind of only sensible if we start the chain in its stationary distribution, not at some random state of our choosing. And the stationary distribution for the case p equals 1 is 1/2 on these two states, and so you kind of start the chain randomly with a coin flip, right? An unbiased coin flip starts the chain in some state, and then it starts moving, and then your task is to say, is time moving forward or backwards? And there is no way to say. So the final answer to this problem, right, would be that the chain is reversible for all p, not just p between 0 and 1. Even for p equals 1, this thing is reversible. And here again, by symmetry, if you want to set p equal to 0, you'll have an identical situation, but on this side, right, for p equals 0, these two states, right, it will form like a local cycle, and it will be impossible to tell which way time is moving there as well. So hopefully this was useful, right? This is from comparing with the previous problem, this was quite a bit more complicated, but and also way less intuitive, right? You still may not be convinced that you won't be able to tell which way time is moving for, say, p equals 0.8 or 0.7 or something, but you can try to code this up and then even run this psychology experiment on yourself. Anyway, I think that wraps up this example. Hopefully this was useful as well.